Hi everyone, it's Professor Pemberton. In this video we're going to look at areas and distances. So in this section we're going to start looking at how do you find the area under a curve, and how does this area under a curve relate with distance traveled by an object, or in particular a car, and we're going to relate them to a special type of limit. So in this section we're going to look at upper and lower sums and how does it relate to area, how to use rectangles with the left or right endpoint, or possibly a midpoint, to estimate the area bounded by a curve, and then use what's called Riemann sums to approximate the distance and the net distance traveled by an object given a velocity function. So we're going to start with the area problem. We're going to start to solve the area problem, which relates the area of a function under the curve. So we're going to look at the area, which is going to be called S, that's under the curve y equals f of x, from x equals a to x equals b, as illustrated in the figure below. Notice that the region S is bounded by y equals f of x above the x-axis from x equals a to x equals b. So you start the area at x equals a, that vertical line. You end the area at x equals b in terms of this figure. We have a continuous function y equals f of x, and the region S is bounded. So the region does not continue indefinitely. It's definitely bounded by this curve, and it's above the x-axis. However, one of the disadvantages of finding this area is that there is no simple geometric formula for calculating a shape where one of the sides or the edges is a curve. But we do know some familiar geometric shapes. We have the area of a rectangle, area of a triangle, and we can even extend the idea to, let's say the shape is this. You could divide the area up into several regions that you can have the area of the shape known, and then you can just add the areas. So the idea comes from the idea of a limit. We first used limits to approximate the slope of a tangent line from the slopes of secant lines. So we took something that was simple, which was the slope of a secant line, the slope of a straight line between 2 points, and then we started to approximate it using a limit. Well, the idea is going to be familiar in this section. We're going to use areas of rectangles and then use a similar process to approximate the area by adding more and more rectangles. So let's jump right into this. We're going to find the area of the region that approximates the region using rectangles, and then we're going to use the limit of these areas of the rectangles as we increase the number of rectangles to infinity. So example 1, use rectangles to estimate the area under the parabola y equals x squared from x equals 0 to x equals 1, and it's represented by this parabolic region S. So notice that we have a quadratic function y equals x squared, or f of x equals x squared, and the area is definitely between 0 and 1. So the area is definitely positive, so it's greater than 0, but the area is not 1 because the area of this square would be 1, so it's definitely less than that. So the idea is that we're going to take this region S and divide it up into sub-regions, and we're going to call those S1, S2, S3, and S4. And each of these sub-regions will have the same width for the base on the x-axis. So let's just make some observations. Notice that the area of S is between 0 and 1. We saw that earlier. However, we can come up with a much better approximation. Okay, the idea is to take the interval from 0 to 1, divide the closed interval, 0 to 1, into, we're going to do at first 4 subintervals, into 4 equal width subintervals. Okay, it just makes the calculations much easier if we use equal subinterval widths. So if you look at this diagram, or the graph, each of these intervals, these subintervals, will all have a width of 1/4. So it helps to draw a number line that represents the closed interval 0 to 1, so that we can see how this interval will be divided up. So we're going to divide this up into 4 equal subintervals. So this is subinterval S1, S2, S3, and S4. Now we need to figure out where do each subinterval stop in terms of x values. So this one is 1/4, then 1/2, then 3/4. We'll come back to this in a second. So let's notice also that the width of each subinterval, or sometimes they might be called rectangles, because we will be using rectangles in this section. Delta x represents the change in the x values, and each width is 1/4. Now, to figure out the area of a rectangle, we also need to know its length, or its height. The height is determined by using the left or right corner of the rectangle using either the left or right endpoint. Of that subinterval. A lot to say just to mean this. Let's talk about using the left endpoints. So if we use the left endpoints, it would be 0, then the 1/4 would be the left endpoint of the second interval, then 1/2 would be the x value there, and then 3/4. Let's look at what it means for the graph. So we're going to approximate the area using left endpoints. So the left endpoint would be 0, 1/4, 1/2, and 3/4. Those would be the left endpoints. The first rectangle would have a height that intersects with the graph. So the height would be 0 because it's right on the origin. Then your first rectangle would just be flat. The height would be 0. The next interval would use the left endpoint where it intersects the graph, and that would be the height of the second rectangle. The third rectangle would intersect at x equals 1/2, so there's the third rectangle. And then the fourth rectangle, same idea, it uses the left endpoint, which is 3/4, intersects the graph, and that's the height of the fourth rectangle. So notice that this would give you an lower estimate or underestimate to the actual area of the region S. Now let's say you use right endpoints. Right endpoints I'm going to use as dashed lines. So the right endpoint determines the height for these rectangles. So that would be the first rectangle. The next rectangle would have a height when x is equal to 1/2. Then x equals 3/4 would be the height for the third rectangle. And since 1 is the last right endpoint, that would determine the height of the last rectangle. So notice that this area of these larger rectangles would be an overestimate to the actual area. So the idea is that we're going to have an underestimate, an overestimate, and then somewhere between the two will be the actual amount of the area for the region S. So let's make all that more formal. So we're going to first find the area approximation using 4 rectangles, 4 subintervals, and left endpoints. So that's a lot to say, but you can denote this by saying it's L sub 4. So L for left endpoint, subscript 4 because you have 4 subintervals or 4 rectangles. The area of the first rectangle would be width 1/4, height f of 0, because the height was determined by the y value at the left endpoint. Next rectangle, 1/4 times f of 1/4. For the second rectangle, left endpoint, 1/4 times f of the third rectangle, left endpoint, would be a half. And then finally 1/4 times f of 3/4. So remember that the function is y equals x squared. So L sub 4 would be 1/4 times 0 squared plus 1/4 times 1/4 squared plus 1/4 times a half squared. You're taking each of these x values and squaring them because that's the function. And this will calculate to be 7/32, which is equal to 0.21875. Keep in mind that this was an underestimate to the actual area. So now let's do an area approximation using 4 subintervals, but this time we're going to use right endpoints. So we drew the picture earlier. We know this is going to be an overestimate. So this is denoted R sub 4, right endpoints, 4 subintervals. The width was 1/4. The height of the first rectangle was using 1/4 for the x value. The next rectangle, width 1/4. The right endpoint for the second interval would be 1/2. And then so on, 1/4 times f of 3/4. And we saw the last rectangle had a right endpoint when x equals 1. So these values go into the function 1/4 squared, 1/4 times 1/2 squared, 1/4 times 3/4 squared, 1/4 times 1 squared. We're finding the y values, or the height of each rectangle, and multiplying by the width of each rectangle. This is 15/32, or 0.46875. So this was an overestimate to the area, as we saw earlier. So the actual area is somewhere between those two approximations. So we know that the actual area of region S is such that L sub 4 was an underestimate, and it was 0.21875. That is less than the area of region S, the actual region, which is also less than the overestimate 0.46875, which was the estimate using right endpoints and 4 subintervals. So this gives you an idea of how to use rectangles to approximate areas. We only used 4 rectangles. They were all equal width, and we were using a very basic function, which was y equals x squared. So this is what we found out. If you use 4 rectangles, the first rectangle doesn't show up because the height was 0. Then we found out the second rectangle's height, and then the area for the third rectangle, and so on. Its approximation using 4 rectangles of equal width was 0.21875, and that's an underestimate. For the area S. And then we also found the R sub 4 was an overestimate, 0.46875. for the area S. So we know it's an underestimate or overestimate based on what areas where the rectangles lie. These rectangles lie completely under the curve, so it's an underestimate because there's these error that we're not actually counting those areas. And then if we use right endpoints, in this case they are overestimates because the rectangles go above the actual area under the curve y equals x squared. So in the previous example, we used 4 rectangles, and we had a lower and upper estimate, as we've seen. But we can repeat this procedure if we use larger number of rectangles. So we're not going to do this by hand. We're going to look at the graphs. The following figure shows what happens when you divide the region up into 8 rectangles of equal width. So each rectangle will have a width of 1/8, and the height is determined by the left endpoint. So the first rectangle doesn't show up because it's also area 0. Then f of 1/8 would be the height of the first rectangle. F of 2/8 would be the height of the second rectangle, and so on. So notice that this is an underestimate still using left endpoints, but it's much better approximation than using just 4 rectangles. We're filling in some of that area that we did not count when we just did 4 rectangles if you use 8. So we have these smaller errors. If you use 8 subintervals and right endpoints, it's again an overestimate, but this overestimate is not as great as it was if we only used 4 rectangles. So if you calculate these areas, L sub 8 is 0.273475. The actual area is greater than that, but it's less than the area using R sub 8. The right endpoints with 8 rectangles, 0.3984375. So the actual area is narrowing down. We knew it was between 0.21875 and 0.46875. Now we have a better approximation if we used 8 rectangles instead of 4. The reason why we want to use 8 is because you can divide the interval up into 8 pieces better than divide up into 6 or 7 equal widths. So the idea is that if you divide the interval into as many subintervals as you would like, but they all have equal width, you obtain better approximations for the actual area. So if you continue this process and you continue to divide the interval 0 to 1 up into either 20, 30, 50, 100, or even 1,000 equal subintervals, and you find their lower and upper approximations using left endpoint or right endpoints, then you obtain these calculations, and it's summarized in the table. L sub n represents the left endpoints using these number of subintervals of equal width, and R sub n is the same for right endpoints. Notice that from using the left endpoints, these approximations are getting closer and closer as you increase the number of rectangles. It looks like these areas are approaching some value. Same for the right endpoints. If you increase the number of rectangles, the overestimate will become better and better to the actual area. So this introduces the concept of a limit. So look at the diagrams. If you have 10 rectangles versus 30 rectangles versus 50 rectangles, the error using the right endpoints is being reduced when you increase the number of rectangles. So we're going to let n approach infinity for this table of values, L sub n and R sub n. We notice that you get closer and closer to the actual area. So these are better and better approximations to the area of S. And so if you look at a limit, we're going to define the actual area to be a limit of the sums of these areas using rectangles, approximation rectangles. The limit as n approaches infinity, so as the number of rectangles increases, using right endpoints, and you look at the number of rectangles approaching infinity for the left endpoints, it looks like these values from the table are approaching 0.3 repeating, or 1/3. And that turns out to be the actual area from x equals 0 to x equals 1 above the x-axis under the curve y equals x squared. So now we're going to apply the idea from the previous example to a more general region S. So we're not always going to be doing quadratic functions. We're going to have a general function y equals f of x. The area will start at x equals a, it will end at the vertical line x equals b, and it may or may not be above the x-axis. So we're going to find the area bounded by y equals f of x above or below the x-axis from x equals a to x equals b. And we're going to divide these regions or these subintervals up into n subintervals. So we have S sub 1, S sub 2, and these are all capital letters for the regions. And these all continue to S sub n, and these all have the same width. So if you divide it up into 48 regions, then each of those 48 regions would all have the same width, just for calculations to be easier. So how do you calculate the width? The width of the interval A to B, that length is B minus A. So if you want to divide this region up into n subintervals or n rectangles to be formed, then you take this length and divide by n. So delta x is b minus a divided by n. That's always going to be the case when we use approximation rectangles. That means this interval from x equals a to x equals b will be divided up into n subintervals. The first subinterval will be x sub 0 or x naught, which is a, the left endpoint of your interval. It will stop at some x value, x1. Then you'll have the next interval at x1 to x2, third interval from x2 to x3, and so on to the last interval from x sub n minus 1 to x sub n, which will be the right endpoint for your last subinterval, which is b. So there's a way to calculate what each of these x sub 1, x sub 2, x sub 3, and so on are. Let's say we use right endpoints. The right endpoints of the subintervals are x sub 1, x sub 2, x sub 3, and so on, up to x sub n is the right endpoint for the last subinterval. Now let's calculate this. The right endpoint for the first interval starts at x sub 0, which is a, and the next subinterval will start when you add in the width. So if you add in delta x, that's x sub 1, which will be the left endpoint of the next interval. X sub 2 would be you start at x sub 1 and you add in the width. And we know what x sub 1 is. It's a plus delta x. So that's x sub 1 is what's in the parentheses. So this gives you the left endpoint plus 2 widths to get to the x sub 2. And then x sub 3 you calculate the same way. It's x sub 2 plus delta x. X sub 2 is a plus 2 delta x. So now it's a plus 3 delta x to get to x sub 3. So this pattern will continue until you get to the last right endpoint, which is x sub n, and it will be calculated as x sub n minus 1, the previous division for the subinterval, plus the width, and that will turn out to be a plus n minus 1 delta x's plus another delta x. So it's a plus n delta x. So one thing to notice is that the number of delta x's is the same as the subscript on x sub I. So x of I just stands for any arbitrary index for the subscripts. So notice that on the third subinterval, you have 3 delta x's added to the left endpoint. X of n, you would have n delta x's added to the left endpoint. Why are we doing this? Well, we're trying to find a pattern on how to add the areas of rectangles when you have n rectangles. So now we're going to approximate the ith rectangle, which is S sub I, with a width delta x, and the height is f of x sub I. So the x sub I is either the left endpoint or the right endpoint, or as we go through this section, it could also be the midpoint of each interval. So it's the value of the function using the right endpoint in this case. And then the area of the ith rectangle is f of x sub I times delta x. So it's the right endpoint, the y value at the right endpoint times delta x. And then you can find the area of S approximated by the sum of these areas of the rectangles. R sub n would be the approximation using n subintervals. So you divide up into n rectangles. F of x sub 1 would be the first right endpoint, the y value, times delta x, plus the next y value for the next right endpoint, which is x sub 2, all the way to the n, the x sub n. So it would be the right endpoint for the last subinterval. And so you can see what the graph is illustrating. You have the right endpoint for your first rectangle is x sub 1, f of x sub 1, that's the point. So the height is f of x sub 1, the width would be delta x. Then the next right endpoint is at x sub 2, so x sub 2, f of x sub 2. So the height is the y value at x sub 2, and the width is again delta x. Third rectangle would be x sub 3, f of x sub 3. And again, the height's determined by the y value, and the width is delta x. So if you do this for all the rectangles, the last endpoint would be at x sub n. The y value would determine the height, f of x sub n, and the width is still delta x. So we're going to add all these areas of the rectangles together. So the following figure shows the approximation with 2, 4, 8, and 12 rectangles or subintervals. Notice that the approximation appears to become better and better as you increase the number of rectangles. So your approximation using right endpoints, notice that the first rectangle may be an underestimate, but also has a little bit of area above the curve. And then the second rectangle is completely below the curve, so it's an underestimate. But then you increase the number of rectangles, your approximation becomes better. So 4 rectangles, 8 rectangles, and then even 12 rectangles. You're trying to minimize this white region, this region that is not being counted for, but it is under the curve, so it actually is part of the actual area. So if you have any questions about any of the examples in this video, please let me know. Or if you have any questions about any of the homework related to finding the area under the curve using approximation rectangles, please let me know that as well. And I'll see you at the next video when we talk about the area problem and define the area and how does it relate to the distance when you're given the velocity function.